All right, everyone. Mr. Bozaday here. We're going to go through the formative and do all the LT5a problems, the word problems. So here we go. The first one says a dumbbell is 30 kilograms. Calculate its weight. So this is a the most simple and straightforward one. It's going to get us to use this equation right here. And remember, this equation says the force, gravity, or weight equals mass times the gravitational field. And on Earth, the gravitational field, G, is always 9.8 newtons per kilogram. So we're going to go like this. Force gravity, which is another name for weight, equals mg. The mass we're given is 30. We know that's mass because it's in the units of kilograms. This is going to be important later on, knowing what those units mean, and kilograms means mass. So Fg equals mg, so we got 30 kilograms times the gravitational field on Earth, which is 9.8 newtons per kilogram. And when we multiply that out, we get 294 newtons. So that's our force of gravity, or weight, is 294 newtons. Like I said, that one is pretty straightforward. I think the most important thing here, and what we're really looking for from you here, is that you understand these units. You understand that when you see kilograms, you're looking at mass. Okay. The next one starts up here, but it ends down there. So I'm going to start up here real quick. Mr. Erdman helps out on Give-a-thon day by pushing a box horizontally in the carpeted hallway past a classroom. He's moving and pushing to the left. We are able to determine that the carpeted surface is rough and causes a force of friction, and that Mr. Erdman's push force is less than the force of friction acting on the box. So we don't actually have to worry about this now. If we were doing this real summative or formative, we would worry about it because we would want to do LT6. But right now I'm just doing LT5. Okay. Okay, so let's start by drawing our free body diagram. Here we go. First of all, we know the box has force gravity, and it's got force normal because it's on the ground. And those two forces are balanced. Some important things that we're told here is that Mr. Erdman's pushing it to the left. See, he's pushing it to the left, and that his push force is less than the force of friction. So we know his force is going to be to the left, force push, and we want to draw that smaller than the one to the right, which is force friction. Okay. Now let's write out our net force equations. The y one's easy because the forces in the y direction are balanced. We've got plus force normal minus force gravity. And since they're balanced, they equal 0 newtons. They kind of balance each other out to equal 0. In the x direction, we're unbalanced. Force friction is greater than force push. So it's gonna equal mass times acceleration. They're not balancing out to 0. So we got plus force friction minus force push, because friction points right and push points left, equals mass times acceleration. Let's go ahead. That's really what we need, this right here, to answer the LT5a. But let's go ahead and fill in this box just for good measure. Let's see. So the box, speaking of box, the box Mr. Erdman's pushing is going left. And we see that the net force is to the right because friction is larger than force push. So we're going to say the net force points to the right. And we know acceleration points the same way as net force. All right, so we're going to jump down to LT5a. All right, so it says we measure Mr. Erdman's push force to be 30 newtons. While we know the force of friction to be 55 newtons, the box weighs 550 newtons. Calculate the acceleration of the box. All right, so what we're going to do is we're going to take this equation we made and we're going to pull it down here to solve the problem. All right, so we'll rewrite it. Plus force friction minus force push equals mass times acceleration. All right, so what are we given? The push force is 30, so and the friction force is 55. So plus 55 minus 30 newtons equals, now here is that thing again, right? Over here, we saw that the dumbbell was 30 kilograms, and so kilograms is a measure of mass. But in this problem, we see the box weighs 550 newtons. Newtons is a measure of force, so that is not mass. So we cannot put 550 in for M or mass. What we can do, though, is we can do a little side work. We can say, okay, Fg equals mg. This is the force of gravity. So we say 550 equals the unknown mass times, and remember on Earth, the gravitational field is 9.8. So we divide the 9.8 over, so we do divide by 9.8, divide by 9.8, and what we see is that the mass is 56.12 kilograms. So 56.12 kilograms is the mass of that box that Mr. Erdman's pushing. Well, now that we have that value, we did that little side work, we can plug it in here. So 56.12 is the mass times acceleration. And now what we've discovered is we only have one unknown. And when we get our equation down, so there's only one unknown, it's just algebra from there. 55 minus 30 is going to give us 25. So 25 equals 56.12 times acceleration. So we divide our 56.12 over, divide by 56.12, divided by 56.12, and we get our acceleration to be 0.45 meters per second squared. So 0.45 meters per second squared is the acceleration. There you go. Okay. So we did our model, and up top, we did our free body diagram. Our free body diagram told us how to write our net force equations, and we took one of those down here to solve the problem. And that's really the way to do it. You got to really, really watch out for this right here. Are we given mass, or are we given force gravity? All right, there's one more of these here. Let's do it. Number 4. A 15 Newton bucket is being pulled up a well with an acceleration of 0.5 meters per second squared. Let's draw our free body diagram here. So we got force gravity down, and I'm going to make force tension bigger than force gravity because we know it is accelerating. We're told it's accelerating. And to accelerate, the forces must be unbalanced. In the x direction, there are no forces, so that's just equal to 0. But in the y direction, we've got plus force tension minus force gravity, and because they're not balanced, they equal mass times acceleration. We know that it's being pulled up, so the velocity is up. We know the net force is up because we see that force tension is larger than force gravity. So we know acceleration is also up because it points the same way. Excuse me, as force net. All right, now let's solve the problem. So we're going to take, our goal is to find force tension, and we see that that is in this equation. So we're going to take this equation we made and bring it down here and solve. So, all right, force tension minus force gravity equals ma, mass times acceleration. Let's see what numbers we have, and we'll plug them in and solve. Let's see. We know it's a 50 Newton bucket. So that is, again, that's that big thing. We need to think about what Newton's telling us. Is it telling us mass or weight? And we know it's weight because Newton's is a force. So that's like force gravity. Force tensions are unknown, so we'll leave that as is. Force tension minus 50 equals, we're going to have to do that side work again because we don't know the mass. We're not given it. So we can go and say, all right, force gravity equals mg. Force gravity is 50 newtons. The mass is unknown, and gravitational field on Earth is 9.8. Divide that over, and we get 5.1 kilograms. So we divide both sides by 9.8, like this. 50 divided by 9.8 is 5.1 kilograms is the mass of that bucket. Okay, now we plug that in over here, 5.1 kilograms, and we're told the acceleration is 0.5 meters per second squared. 0.5. Oops, there we go. So now it's just algebra again. When you only have one unknown, it's just algebra. So 5.1, we'll multiply these two together. 5.1 times 0.5 is 2.55. So force tension minus 50 equals 2.55. Then we will add 50 to both sides, right? To move it to the other side. So we get force tension, and this can be our answer. Force tension equals 52.55 newtons. And there you go. Now we're done. And so just like the last problem, the steps were the same, right? We started with our free body diagram. Our free body diagram let us write our net force equations. We pick one of them, bring them down here, and we solve using algebra for our final answer. The only thing you got to be careful of is this. Do you have to do some side work to solve for your final answer? All right. Hope that's helpful. See you later.